Thank you so much for your patience. Would you mind sharing your screen? So it is my honor to introduce Professor Adelson. I don't think he needs much introduction. He has been referred to entire day. So I think with a little bit of short of touch, I'll let you get started. Thank you.
Thank you. Can you hear me okay?
Yeah.
Okay, great. So I thought it was a good time to think about where the future is going. Because there's so much activity in camera-based sensors these days, and I'm excited about the possibilities. Here's an example of all these different camera-based sensors that have been developed recently, and more continue to be developed. And another bit of evidence for the excitement around camera-based sensors is that lots of people are putting up open source repositories for the hardware and the software. Nathan Lepore is one of the pioneers of doing this, but we're seeing other people. Roberta Calandra is doing this both with hardware and software, including this simulator. People in Alberto Rodriguez's lab have put up stuff for their Gelsite 3. Just recently, the people at Toyota Research Institute put up stuff for their inflatable soft bubbles, which is a very interesting alternative way of doing camera-based sensing. So there's a lot of excitement and a lot of forward motion. So what's so good about camera-based sensors? I guess I don't need to convince people here it's good, but it's worth reminding everyone of some of the problems that you encounter with other kinds of tactile sensors. You've got some material which is doing transduction, like resistive or capacitive material. And that stuff is touching the world, and electronics in direct contact with the world really isn't a good idea because it tends to break. You have to make it soft. That's not so easy. And you have to get all the data out with a lot of wires. That's not so easy. But with the camera sits far away from the contact point. There's just one big wire coming out the back. And there's no loss of resolution when you use something soft because the camera is seeing everything. It's seeing all the data coming in from the contact. So it's really a wonderful combination of properties. And the main problem with cameras is that they take up space and they limit the configurations you can do. So I'll talk about work we're doing on that. But as far as what the future holds, I'm quite optimistic. And it's interesting to compare, just to think about what's happened in 3D sensing for robotics. It used to be if you were working in robotics, some poor graduate student would spend their entire graduate career putting together a stereo system so the robot would have 3D vision. Lots of people worked on that, and now you just go buy something, and it's not expensive, and it's easy to use. You just get a depth camera. Nobody even thinks about it. Hopefully that time will come reasonably soon in touch sensors. Certainly we're not there today, obviously, but I can imagine in a few years, we will be at that point where there are these sensors that just work reliably, and you don't have to devote a graduate student to make them work. Okay, how about Gelsite? I think many of you know about it. It turns a mechanical signal into an image. It uses a shading signal. It's the deformation is what you're detecting by this optical method. You can use photometric stereo to get 3D. You could also use other measurements, other ways of getting depth, but anyway, that's our favorite. And the potential resolution is really incredible. In fact, when we started a company, Gelsite Incorporated, we looked at various markets, including robotics, and decided there wasn't a robotics market, but there was a good market in metrology or profilometry, meaning measuring the microgeometry of surfaces, because you can get measurements down in the micron region. And so that's what the company has been selling. But now, finally, it's looking like the robotics market is interesting enough that it's worth getting into. And the company will be introducing some sensors that hopefully some of you will find interesting enough to buy. And we're looking for feedback on what is valuable to the robotics community. Anyway, so how can we make the camera-based sensors useful in robotics? When we first started out, our sensors were quite bulky, and we're learning to get them into nicer shapes and smaller sizes. And there are all these other things you'd like accurate sensing. They need to be integrated with grippers, which can be a challenge. Also integrated into the control systems, of course, that's critical as well. And like everybody else these days, we're finding that deep learning is a great tool for making them useful in alternate ways. And I want to mention something special about camera-based sensors that's not obvious, which is that their native language is geometry. That's what they're good at measuring. People like to use them. People like to use touch sensors to measure force, and you can infer force from the changes in geometry. But many times that's not what you need. Many times geometry is actually just what you need. And if you imagine yourself holding a pen, what are you feeling with your fingers? You're feeling its shape, its pose, its compliance, its texture, the way it's moving, whether it's slipping, and also the force. And all of these things can be inferred either directly or indirectly from the geometric data that the sensor is providing you with. And sometimes that's not obvious, but if you just look at the picture, it becomes obvious that slip is something you can measure by tracking the geometry over time. And I think even less obvious is something like hardness. Hardness really seems like something that would need force in order to be measured. But it turns out that you can measure hardness by just with geometric measurements. And so here's on the left is a ripe tomato being smushed against a gelsite pad. And on the right is an unripe tomato, a hard tomato being smushed against it. And what happens is the hard tomato stays in its original shape. It does not deform, whereas the soft tomato flattens out as you press it. Hard tomato remains spherical as you press it. And basically the soft sensor and the soft tomato engage in a competition to see who's softer, and the one who's softer deforms more. So you can get hardness and softness from geometry as long as you do geometry over time. Here's Wedge with avocados, and we did some machine learning to get these numbers. The number isn't meaningful, 84.6, but the point is that we can place the avocados in the correct order of hardness just by feeling the way the shape is changing as we press against them. Now the most popular, in our lab, the most popular shape we've been using is a wedge shape. I'll be giving you various examples of that. And recently, Sean Wang has been perfecting our wedge, which he talked about earlier this week at ICRA. And the wedge is an attempt to get the best of both worlds from the work we've done with the original Gelsite sensors and the GelSlim sensor that we've worked on in collaboration with Alberto Rodriguez's group, and which they've since then developed further. Anyway, here's one of our wedges, a slight variation on the one that Sean's been using, but we've used these little ones for cable manipulation. Now, that's a really interesting and challenging problem. And again, this is work that's also in collaboration with Alberto's lab. And here's the problem that we're going to work on. Suppose you want to stick the 3.5 millimeter plug into your phone. You slide along the cable with your fingers and then reorient the pose so you can get it in the hole. And so there's a lot of tactile tasks here. And if you want to do it at any reasonable speed, you want a nice, pretty fast control loop. So you need not just a good sensor, but a good gripper. And so we built a fast gripper here, which has a 60 hertz bandwidth. If you're going to do a fast feedback loop, you need to have not just fast sensing, but also fast actuation. So it's lightweight. The sensor and the gripper is lightweight and can move quickly. And here, here's the gripper holding a cable, and you can see we're getting data out of the sensor. We get the pose, we get the force, we get both the normal force and shear force. And there's two kinds of control running in parallel here. One is, in order to allow the stuff to slip between your fingers, you have to hold it just right, not too hard, not too soft. So that's the first thing we're controlling, is constantly keeping track of how hard we're gripping it so that it can slip the correct amount. And then the second thing is controlling the pose, because it's threatening to slip out of your fingers because it's moving across. You've got to predict where it's going to go depending on how you move your arm to keep it in place. And we use an LQR controller for that. And so here it is. It is moving. It's a wiggly shape, so it has to move in order to keep track of it, to keep it in place. And it needs to be able to hold it just right so it slides nicely, so we're getting good tactile data. And it works. We can try to disturb it, and it'll respond appropriately and reasonably quickly. And then we can put everything together. We're also adjusting the pose here. We assume we already know where that hole is that we're sticking the thing in. But each time we have to adjust the pose a little bit, because each time it grabs a little bit differently, but it can figure out how to adjust the pose. So as it goes along, it adjusts itself to keep hold of the thing, and it adjusts the pose at the end to get it in the right place. So we can do this entire little piece of dexterous manipulation by combining a nice sensor, a good control policy, or two control policies, and a gripper that moves along quickly. All right, next up, let me tell you about SwingBot. This recently won Best Paper Award at IROS. This also uses wedge fingers. And here's the task. You want to swing this thing up like this, like you're holding a pen and you're flipping the pen up in the air and trying to get it at a particular angle. Now, we'd like to do this with reactive control, with feedback, but our feedback isn't fast enough. So we're actually doing it. It's an open loop thing, but we calculate all the parameters ahead of time using tactile data. And the interesting challenge is that we don't know what pen somebody's going to give us ahead of time, and we don't have any vision, we're just using touch. So for a single pen, give me a single pen, fine. I can fiddle around with the parameters of the trajectory and get it to kind of do the right thing. But now you give me a different pen and I'll have to completely rechange all the parameters because it'll have a different mass, different friction, different center of mass, and so on. But if you're a human and I give you a pen and I say, flip this thing up, what you'll do is you'll sort of wiggle it around and get a feel for it. How heavy is it? How slippery is it? And then you'll, do your thing. So the question is, can we teach a robot to do the same thing? Can it grab hold of it, feel what it feels like, and then do that trajectory? And we use these, so here's the wedge sensor, which you know about. Here it is with the finger smushing on it, and here's what you can see when the finger is smushing on it. All right, so what our SwingBot is, did I skip something? No, I guess so. All right, so this is what it's going to do. Its goal is to flip it up like that, but it's going to do tactile exploration. It's going to first shake and tilt the object to assess its physical properties before it tries to do the swing up process. And so here's our pens, if you will. They have different masses, different frictions, depending on what materials we put on them. So there's 4 parameters. If you were going to model this physically, you'd need these 4 parameters: mass, center of mass, moment of inertia, friction. We don't know what those are. And the robot doesn't know what they are. But the robot is going to learn the relationship between whatever it feels and its success at doing the swing up. So you run it overnight with a bunch of different versions of the pen, and each time it feels what it feels like, and then it attempts to swing it up. And then we've got a camera that watches to see if it's swung it up correctly. And at the end, it has learned the relationship between what it feels and the way it has to do this swinging action. And again, it doesn't actually know any of the physical parameters, any of the parameters a physicist would use to describe it. It just knows what it feels like. That is, it just knows the tactile data it's been getting. Let's go by. All right. So let's look at these tactile explorations. So that's tilting. It gets these essentially measurements of torque. Both torque and force show up in these measurements. Again, it doesn't know anything about torque and force specifically, but it has these measurements. And then it shakes it, and again, it gets these measurements of how the thing is moving while it's shaking. And that's the raw data. And throw everything into a neural net. I'm not an expert in learning, and I'm fortunate to have students and postdocs who know how to do this. Anyway, so what have you got? You've got these signals. They're going to go into their little net, piece of the net. You've got this signal. It's got its little piece of the net. Everything's getting digested down to a smaller dimensionality. That all gets combined into something even smaller. And then we also have the data about what the robot tried, how it tried moving it, and what happened. And so that's the entire chain of information that is used to train the system to figure out what is the right way, given the way this thing feels, what's the right way to swing it in order to make it swing up to the desired angle. And the answer is magic, it works. So there we go. Different objects with different friction, different center of mass, moment of inertia. It figures it out just by feel. Again, it's not using vision, it's not using anything, not using any knowledge except its own experience. And these are, by the way, it's doing this with novel objects, not ones that it already felt before. And what's really interesting is you can look inside the embedding and see it has structure that tells you that it is implicitly pulling out the information you need. Remember those 4 parameters: mass, center of mass, moment of inertia, friction, which we don't know values for that. The robot doesn't know values, but it is implicitly pulling out things that essentially map onto those in order to use it for this task, which is the same way a human would do it, right? If you learn to do this, you as a human learn to do this, and I ask you, oh, what center of mass do you think this thing has? You'll have no idea, but you will have learned this mapping from the way it feels to the action you need to do. All right, so we can use these tactile exploratory procedures to pull out these physical parameters, they're implicit physical parameters, and use machine learning to learn to map those feelings into the correct parameters of the trajectory. So let me tell you about some other things we're working on, other configurations of the fingers. A lot of people would like to have round fingers, like you could use on a Allegro hand. And when he came into the lab, Philippe Vega said, I want round fingers on an Allegro hand. So we got an Allegro hand, and Philippe and Brandon Romero started working on how to build fingers that could go there. And if you just try to make a Gelsite finger that's round, it doesn't work very well because the lighting doesn't work. It doesn't give you the kind of grazing angles that you need in order to just see nice information about the shape of the object. So in order to get the illumination moving directionally, we came up with a light piping configuration where the Gelsite is, there's a hollow shell, it's a rigid shell, and the gel is layered on top of the shell, and the light runs along under the shell and bounces around inside. So wherever it is, it's directional, it's running along sideways, and we bring in light from 3 different directions and 3 different colors. So we can get the sort of image you see on the right, which gives us the kind of shading information we need in order to get 3D depth out of it. And we will in the future use this for all kinds of wonderful things. At this point, the most interesting thing I have is a demo that Brandon put together. It's not published yet, but it's so cool, I want to show it to you. So here's the Allegro hand equipped with its round fingers. And over here on the right, you can see that's the data, that's the raw data actually coming into the hand. Brandon is going to toss a jar in there kind of randomly. So he doesn't place it at any exact place. It's just casually placed in there. And now the hand wants to remove the lid. There's no vision, so it doesn't know exactly where anything is. It can only tell by feel. And as it's feeling, the jar is moving around because it's not held down. But it is able to figure out what to do through the clever control strategies Brenda came up with. See that again. So it's just casually placed in there. The fingers have to figure out, oh, where is it? There it is. Am I in the right place? No, let me move a little bit more. I'll move a little bit more, and eventually it starts to feel like, oh, it's moved, and it's moving in such a way that it feels like it's loose. So now it's time to pull it up. So that's all done autonomously, even though, of course, it's specially written by hand for this jar, but the whole thing's run autonomously without feedback from vision, just the feedback from the fingertips. All right, one of the problems with camera-based sensors is that it's hard to put them in fingers other than in fingertips, especially with existing fingers. So on the left, there's a shadow hand, and we've thought sometimes about how would you put Gelsite into the fingers, not just the fingertips, but the whole finger. And you can't do it because there's stuff there. The people who built the hand put stuff there. It gets in the way. So that really is the limitation that cameras have. You can't just, you would like to be able to just paint skin on your finger and have it work magically. With a camera, you have to do something more roundabout. And so in the last talk, you saw some ways you can get non-camera based fingers to get interesting shapes. Anyway, what we've done is said, let's make our own fingers starting from scratch, not try to retrofit somebody else's fingers. So on the right there, what you see is an exoskeleton. The black stuff is an exoskeleton. The yellow stuff is a slab of gel covered with this yellow material. And that's all clear. All the stuff inside the exoskeleton is clear. And so you can stick a camera or two inside. If it has a fisheye lens, it can look around. So you can see everything inside the finger. And this is an under-actuated finger with a tendon driving it. So you can, and we've got two of them on either side. So you've got a gripper that's got two fingers. Both of those fingers have cameras inside them that can see all around. And when they look around, they see two things. First of all, along the edges of those slabs of gel are a bunch of dots. And by looking at those dots, you can get proprioception. You can figure out the three-dimensional configuration of the finger. And then along the front is some reflective material that gives you a shading signal, like Gelsite, so you can get a tactile signal along the front. So it's a nice way to exploit the information you can get from the camera. Namely, you can get the tactile data, and you can also get proprioceptive data because it tells you about how the overall geometry is changing, which of course is going to be necessary if you're going to make good use of the tactile data. And so this is our initial attempt to build our own fingers. We're going to continue this kind of project in the future. We've got some funding from Toyota Research Institute recently to build hands that can have this sort of sensorization. Can you do other things? Well, here's a Finra finger. We're just starting on this. Sandra Liu is shown there on the left. Finrays are nice because they automatically hug the object that they're grasping just by the passive nature of their mechanics. Well, we can't stick a Gelsite sensor on top of one, and we can't stick a camera inside of one because the stuff is in the way. So we are trying to make Finrays that will behave the right way but don't have so much stuff in the way. We can move enough stuff out of the way that we can get a camera in there. And Sandra has some initial results that look promising. On the right, you see the fisheye lens looking at a screw being pressed against it. And you can imagine this would, this could greatly improve the utility of a Finra Finger. Another finger we've recently been working on, we call the Digger Finger. We have some sponsorship from ONR, the Office for Naval Research, to find buried things like buried cables that might be attached to roadside bombs. And the problem, of course, is that our traditional Gelsite sensors aren't very good at going into sand. They're too bulky. So we've built this one with a tapered tip that will penetrate granular media more easily. And basically, you take a cylinder, slice the tip off at a bevel, stick a mirror on that bevel, and then stick Gelsite around the perimeter of the cylinder. And there's a camera looking down the bore, bounces off the mirror, looks at the cylinder, and sees what the Gelsite's seeing. This one also has a clever illumination system. There's only one color of LED, which is blue, which is shining down along the bore axis. And then on the left, you can see there's fluorescent paint on the edges of this acrylic cylinder that's holding the whole thing. There's red and green, and the red and green conveniently will fluoresce when they see the blue. So the blue shines down there and does two things. It provides blue light in one direction, and it provides red and green light in other directions through the fluorescence. So that's nice because we can get the LEDs away from the tip where they might get damaged. Anyway, we can get it into sand, and the picture in the middle shows it going into sand, and those circles on the right show what it sees when there are various objects underneath. There's another trick on this that Nancy Ouyang came up with, which is if you put a vibrating motor on the whole thing, it gets through the sand more easily. And up above, the dark line shows the amount of force that's needed to get a certain distance into the sand without vibration. And then the other lines show the improvement. It's much easier to get in if you have vibration. Anyway, so this is a cool combination of technologies where we've managed to make a Gelsite finger that's useful for this application. Okay, but in spite of all this, we keep coming back to the Wedge and trying to figure out what's the best we can do with it. There's the Wedge. It's got lights coming from three directions. It's not optimal because it would be optimal to have them coming at 120 degrees so they're evenly spaced, but they're not optimal. But the question is, how well can we do even though they're not optimal? The answer is we can do quite well using a combination of photometric stereo and some model-based and some neural nets. We can also make it smaller. This is a prototype we will be exploring in the future. We can get it down to finger size. One of the problems always is robustness. When you use these things, for example, if you're doing the SwingBot and you're training it overnight, it tends to wear out because that's a lot of shearing motion that's abrading the skin. So can we make it more resistant to abrasion? That's always a problem for touch sensors. If you want to have them in industry, they're going to have to run 24/7 without wearing out. I'm pleased to say we're making some progress. I'm working with the people at the company on some new materials, which we'll eventually describe. And one of our tests is we place the sensor against a bandsaw, not a bandsaw, sorry, a belt sander, which is crazy, and see how long it will last. We're pressing it gently, but nonetheless, it's crazy to press one of these things on a belt sander. But we do have materials that will last for a few minutes. So that's very exciting. And just getting back to what kind of accuracy we can get out of the wedge sensor. This is from Sean's talk earlier this week at ICRA. Here he's got the dots here, but he gets rid of the dots. He has a way of getting rid of the dots so he can get a nice accurate 3D reconstruction at the same time that he's getting all this information about the shearing displacement. And here's my favorite demo from that paper, which is there's a cube. Here's a model of the cube. We assume you know what shape the cube is, and we assume you know that it's yellow. But you've got this data here, and you try to infer the pose of the cube and do that in real time. And so here, Sean is wiggling the cube around, and all the data is here. This is all the information that he's getting out of the sensor, but it's good enough to really track the pose of that cube. All right, so let me summarize that. The future looks bright. I think Gelsite and other camera-based sensors are flourishing. We can make them in many sizes and shapes. You can use them for all kinds of useful things, inferring material properties, inferring pose, inferring slip, using them in control loops. And we are going to try to commercialize these. We'll see how they do. Sometime this summer, hopefully, we'll be releasing some beta versions to get people's impressions. Please let us know what you think would make a good touch sensor, and we'll take that into account. That's it, and thank you very much.
Thank you. Excellent. Thank you so much. Wonderful work. Excellent history of work. I now open to questions. Anybody? If not, I will go. So, Shane?
Okay, I can start the questions. Can you hear me?
Yeah.
Okay, great. A very impressive talk, Thijs, very inspiring. So you have shown a series of tactile sensors. We have seen these finger shapes, we have seen these wedge shapes. So in your mind, what is the best shape and what limitations we have got for now?
Well, in our lab, the most popular and versatile shape is this wedge. You know, we really want to know what other people want. Certainly, there are some people who want things like the BioTac, which are really small and shaped like a finger. And there are people who want stuff that covers the entire hand, which we're not good at doing yet. We're making steps in that direction. There's some people who want fingers that are completely round. There's like cylinders that are completely round. We're working on that, but we don't have a good one yet. So I would say there's no single best answer, but for the work we tend to do in our lab right now, the wedge is a good compromise. It's accurate and it's fairly small, and the shape we've found to be a good shape. By the way, one thing we've found, I think other people have found as well, which is that flat sensors, which seems like maybe it would be a good idea because a lot of grippers have flat fingers. Flat sensors are just terrible because unless you're perfectly aligned with the thing you're touching, you can't feel anything. It hits the edge. So slightly rounded is necessary for a good touch sensor. Maybe fully rounded, like human fingers, may be even better.
Wonderful. If there's no, I'll jump in. I'm gonna go off the topic a little bit. My dear friend Chris Atkinson, I'm not sure if he's in the audience. Him and I love Baymax. Right. So can you imagine building a Baymax with tactiles?
Yeah, I mean, it's not something that we would do with Gelsite because you don't need that kind of resolution. But I mentioned earlier, the people from TRI have been working on these soft bubbles.
Yeah.
And they've released this open source material on them. And I think that the soft bubbles have great possibilities because inflatable stuff is it's incredible. It's really lightweight. It's really strong. I mean, you can build these bouncy houses for kids' birthday parties. You can you build an inflatable kayak. You can build it in all kinds of shapes. You can have it all smashed up and then deploy it wherever you are. So I think that there's great possibilities there.
Yeah, I carry a soft robot in my backpack. That's for a different experiment. But what about multimodality? How would you foresee that?
Within the finger?
Yeah.
Yeah, that's a good idea. So we do not have temperature. We should have that. Someday we will. We do not have vibration. We should have that. Someday we will. I think those things are important, especially vibration.
It's really useful. It's very useful.
Yeah.
So we do multimodality with vibration, temperature, and force.
Yes. Yeah, those are definitely. We definitely need those things.
Do you think you can do proximity?
Francois Hogan, you might know, he's built a version of Gelsite that's transparent, semi-transparent, so they can see through it. It's sort of like a blend between Gelsite and finger vision. You can see through it, and you can, if you turn up the lights on the outside, you see the world. If you turn up the lights on the inside, you see what's inside. So it gives you both. It's very clever, and I think it might be a very good way to go.
Okay. Okay. I think I can imagine a Baymax like that.
Yeah, sure.
Yeah. So is there any other question?
Can I ask a question?
Yeah, please.
So thank you for the talk. Wonderful results. So impressive. And just the quality of the data from these sensors is just amazing. It's incredible. It's essentially unbeatable. And then, this is why we often come back to the shape and size, which you also talked a lot about. So I was wondering, can you imagine maybe even an automated design tool? I mean, the building blocks, right? You have the camera, you have mirrors, you have internal reflection. Can you imagine? And right now it seems that if somebody asks for a different shape or size, and they say, this is the area that I want sensed, you need somebody that comes in and thinks about it. You have this human expertise to see if it can be designed. Can you even imagine just automating that process and somebody saying, this is the shape of what I want sensorized, this can be blind. Can you come up with somewhere to place the sensor? And can you even think about automating that process so that we can just dream up new shapes and sizes very easily?
So that is a very important question, because right now our process is extraordinarily painful. You have an idea, you physically build the thing, you try it out, it doesn't work, you tweak it, you build it again, it doesn't work. But you should ask Wenjen, because she is putting together a simulator. Other people have put together simulators, but they're simulators for fairly simple situations. But Wenjen is, with her students, is putting together a simulator that will allow us to really do fairly complicated shapes and do it accurately, which is what's needed. It's a very complicated problem because the way the light behaves is actually quite complex, and the materials, like if you have the way the pigment reflects light is complex. So it's not easy, but it's very worthwhile doing because I think it'll make a huge difference, and hopefully we'll be hearing from her soon about successful steps forward in that.
That would be incredible, because if you have a simulator, then you can also train policies in simulation with these sensors. That would be really amazing. Very cool. Thank you.
That would be very cool, actually. Okay, is there any other questions? Oh, that's wonderful. I hope we can get in touch with Gelsite Inc. to get some more sensor to play with. I think many of us are looking forward to playing with your sensor. And thank you so much for the amazing talk. And then I hope you can stay with us a little bit longer and answer some of the questions online in the chat. And then I'll move into the next session. Thank you so much.